Hi everyone, welcome to today's Dublin FameLab event. My name is Fergus McAuliffe from iCrag at UCD and I am a FameLab alumnus. As you know, FameLab is a global science communication competition run by the British Council and Cheltenham Science Festival. This is also the final year for FameLab. My FameLab journey started in 2013 when I took part in the inaugural event. Winning that event and then going on to win the international event opened up a whole new career in science communication to me. It's a creative and exciting field and one that I still work in today. I have no doubt that tonight's participants will receive as much enjoyment from the FameLab experience as I have, and I'm now very pleased to pass over to our host.
Hello and welcome to FameLab 2021. I'm your host for the evening, Adam Murphy, and we are gearing up for the national final with the first of our two Dublin heats. The second heat will be broadcast on the 24th of June. Now, we are in the 9th and final year of FameLab, and I've been part of it since 2014. It's part of the furniture for me at this stage, so I'm really going to miss it. But we've got a whole new group of people who will be giving their talks and will be going on to the next one. The rules for FameLab are quite simple. You have 3 minutes to give your talk about an aspect of science, any aspect of science, and you are not allowed any PowerPoint, and all you can have are the props that will fit on your screen. That sounds like not a lot of time and not a lot of rules, and it's less time than you think it is. So it's a lot of nerves, so please be kind to our contestants. The other key thing, of course, is that we have judges. Someone has to win. The judges will be judging on 3 particular criteria, and that is content, clarity, and charisma. Content is the science correct? Doesn't matter how good a talk it is if it's wrong. Clarity is how well do you understood it? Could you follow it from beginning to end, or did you go glassy-eyed and zone out far into space? And the third is charisma, which is, well, was it charismatic? It's that thing everyone says is important and no one can define particularly well, but you do know what it is when you see it. And we have 3 judges who will be joining us today to do this and this very important job. The first is Maria Delaney. Maria is an investigative journalist for Noteworthy, which is a project by the journal.ie to support in-depth reporting. She is an award-winning science and health journalist and previously worked as a freelancer for national newspapers and radio. Maria, could you give us a quick wave there? Brilliant. Good to have you on board with us. The second judge we've got is Owen Murphy. Owen is a biochemist, educator, and science communicator. He is a winner of the Mary Mulville 2021 Science Communication Award for an audio documentary and former winner of the HEA Irish Independent Making an Impact Award. Having returned to education, Owen is working on innovative means of bringing science communication to secondary schools as well as the wider general public. And could we get away from you, Owen? Good, you're on board as well. Yeah. And last but very much not least, we have Aisling Murray. Aisling is currently head of programming at the Science Gallery Dublin, where she manages creative programs converging art, science, technology, and society from concept to full realization in Ireland and internationally. Aisling has over 10 years of experience as a curator and creative producer with projects outside her current work, including in Turkey Design Week, Galway Theatre Festival, Project Arts Centre, and the Dublin Fringe Festival, among others. Hello, Aisling. That is, I think you'll all agree, 3 very qualified judges to be taking on our contestants. What's going to happen is you will see our video from our contestants giving their talk, and then we will move to the judges, and the judges will have 2 or 3 minutes to converse with our contestants and get their teeth into the subject in a way everyone loves listening to, but is terrified to be subjected to. So again, please be nice to our contestants. We have various socials that you can engage with, so please do. There's a Facebook chat that you can get part with. And if you're on Twitter, the hashtag is #FameLab, and the @ is @FameLab_Ireland. Please, thoughts, ideas, anything that comes across your mind about the contestants and how great all of them definitely clearly are, please add it to that and let us know. So then, without further ado, let's move on to the first of our contestants. We have 8 of them tonight, and they are all geared up and ready to go. The first one is Rhea Zwane. Rhea is a South African PhD student that came to Ireland to pursue her PhD studies at Dublin City University. Her PhD project is in computational chemistry, and in her spare time, Rhea enjoys the sea, writing, and conversation. And her talk tonight is called The Chemistry of Shape in Chocolate and Drugs.
What do you love the most about your favorite chocolate? Is it the shiny brown color? Or maybe the snap? Or is it maybe the melt on the tongue? Well, the taste, appearance, and texture of chocolate has a lot to do with chemistry. The molecules of cocoa butter used to make chocolate can arrange themselves in different ways or crystal forms. In one crystal form, they can pack in one way, whereas in another crystal form, they can pack differently. And we call these different crystal forms polymorphs, meaning many shapes. Chocolate has up to 6 polymorphs, but only one of them is able to give you that shiny chocolate with a good snap and a melt on the tongue. But how do we make sure that we get the correct crystal form? Well, the easy answer is that the chocolate maker has to make sure that chocolate is produced at the right temperature, and they have to check repeatedly. They also need to make sure that chocolate is packaged correctly for storage. But even with the correct polymorph, chocolate can slowly transform into the less desirable crystal form. You know that whitish, grayish coating on your chocolate? One way that this can happen is if you leave chocolate for far too long in your cupboard, the right polymorph can slowly turn into the less desirable one. Another fast way that this can happen is if you leave chocolate in the trunk of the car, it can melt and then cool into the incorrect crystal form. The same chemistry also applies to painkiller tablets in your medicine cabinet. Like with chocolate, painkillers can exist in different polymorphic forms. But polymorphism can be a little bit serious for drugs, as you can imagine. The wrong polymorph can mean shorter shelf life, but also it can be slow to heal your headache or not at all. The wrong polymorph can also affect tablet formulation. Paracetamol, for example, has up to 3 known polymorphic forms, but only one of them can form a smooth, stable tablet, whereas the other one forms a crumbly tablet with poorer qualities. Like with the chocolate maker, the chemist has to make sure that drugs are packaged correctly and stored in a cool, dry place instead of a trunk of a car. On one hand, polymorphism can be a huge challenge in drugs, and choosing the correct one is very important. But on the other hand, the discovery of new polymorphs can actually mean better drugs with less side effects. Both chocolate and paracetamol are known to relieve pain. Paracetamol can heal your headache, and chocolate, that special kind of pain, which is a heartache. But another commonality between the two is polymorphism.
Rhea, thank you so much for that. I am a fan of any science that is going to involve making my chocolate better than it was before. And also our drugs too, I guess. Now let's bring in the judges for the first batch of questions from them. I think Aisling, you're first on my screen. So what did you think? Any thoughts?
I was delighted you were coming to me first. Well done. I really enjoyed that. And I liked the use of the props. I suppose my question, it might be a really obvious one, but is which came first, the chocolate or the drugs when you were approaching the storytelling?
It certainly was a chocolate because I had experience of having chocolate melt when it was put on a hot day. And then I thought, why is it that when my chocolate cools, it doesn't taste quite different? And so I just looked it up, and it turns out that years later, my project is dealing with the same concept, which is polymorphism.
And then Maria, what about you? What are your thoughts?
So you're saying your project in polymorphism. So I presume a lot of research in this is done in drugs, as you're saying, but is there anything that we can learn? You kind of touched on some of the points there, but from what we're learning in drugs to make our chocolate better, more importantly.
Yeah. So I guess so chocolate is also, a lot has to do with chemistry, but also a lot of it has to do with the art of making chocolate, which a scientist can, has nothing to do with it. You don't have to know the science really to make a really good chocolate. And so the quality of it has to do with you knowing how the process works, knowing what to do at the right time. For example, with the processes, whether you mill your cocoa bits for too long or not for too long. So I think the polymorphs that we know of chocolate, which there are 6 of them, they could be the ones that we that are out there, and one of them is able to give us the quality of the chocolate that we know and love, and the rest is just art, I think.
Brilliant. Thanks very much. I think we will protect Rhea from any further questioning, and I think she smashed that as well. Thank you so much. Right. Well, that's the first one down, and I think we've set a good standard for the evening, haven't we? That was brilliant. We'll move on to contestant number 2 now. And our second contestant is an undergraduate student in Dundalk Institute of Technology who's interested in the fields of genetics and how environment and behaviour can change the way our genes work. Her name is Angelique Sherrill, and her talk title is called Tanning, Beautiful but Harmful.
A lot of people are obsessed with getting tan skin, but do you know that it is actually very dangerous to your skin because it can cause your DNA to break? When your skin is tan, it is actually giving a sign that your DNA is already being damaged. And the UV rays from the sun is causing this damage, especially UVB. Well, UVB is indeed known for the production of vitamin D, which is very important. But here's how it can cause us such malicious damage. When your skin is exposed to the sun, UVB penetrates into your skin cells and it is absorbed by a specific base in your DNA called thymine base. This thymine base will absorb this UVB, and due to this high energy, it causes the bond within the DNA bases to break. And instead, it will bind to another thymine base next to it, creating a kink. And this is an error that we do not want, because it can lead to harmful mutations such as skin cancer. But hold on, this is a common scenario and we do get this all the time when we're exposed to the sunlight. So do not need to worry too much about it yet, because a little bit of this error can be fixed by our cells. What we need to be worried instead is when our skin starts getting tanned. This is because it means that there's too much of these kinks in your DNA. And when there's too much of these kinks, your skin is actually stressing out because of this high intensity of UV rays that it is exposed to, which is more than it can handle. That is why it is triggering brown pigments called melanin to be produced. These brown pigments are causing your skin to appear tan. And people with fair skin tone have naturally less amount of melanin compared to people with darker skin tone. That's why they're more prone to skin cancer. This is because melanin gives slight protection from further DNA damage, because it absorbs some of the UVB that penetrates into your skin. So most people think that tanning for a good few hours is a good reason to get vitamin D. And now you know that it is not. Small doses of sunlight is enough to create vitamin D, but larger doses attack your DNA. So why don't we just embrace the natural beauty of our skin tone? And don't forget to put a shield on against these UV rays, which is your sunscreen.
Is anyone else the kind of person who just doesn't tan, just burns, and then just feels bad? Well, I am, at least. Anyway, I thought that was brilliant and yet another reason to wear sunblock. So let's bring Angelique back and into this chat for a chat with our 3 judges. So here we all are. Owen, I'll start with you. Any thoughts or questions?
Yeah, thanks, Adam. Angelique, a really important issue, I think, the topic that you took on. And I was just wondering, I mean, you know, we've known a lot about the causes of skin cancer for a long time. And do you think science communication, is it a way to really get the message across to people that, you know, it's really important to protect your skin?
Yes, so I know a lot of people are obsessed with tanning, and somehow they also know that this is actually dangerous. Like, too much exposure to UV rays can cause skin cancer. But I think they're not aware, like, the ugly truth behind it, like how aggressive this UV ray can actually cause skin cancer in just one indoor tanning session or a few outdoor tanning sessions. So to make people more aware of what is actually happening inside our skin, I think it is pretty clear that the damage that it is causing is not worth the beauty. So yeah.
Thanks, Angelique.
And Maria, we have time for a quick question from you.
So you mentioned, and well done, that was really good. You mentioned UVB, and that's what penetrates the skin. Like, do most sun creams have kind of UVB protection, or what can people do, I suppose, to stop having this damage to their skin?
Yes, so sunscreen is one of the best ways to protect our skin from UVB because it absorbs UVB. And the other way is to wear long sleeve clothing or good fabric, because fabric can actually also protect your skin from UVB.
Brilliant. Thank you very much for those brilliant answers and great questions. Thank you all. So we'll keep this excellent ball rolling with our third contestant. And now let me make sure I get his name right. His name is Adam Stapleton, and he is a PhD candidate at ML Labs in DCU with a background in theoretical physics. Adam's broader research focus looks at the application of ML techniques to climate change related problems across understanding, mitigation, and adaptation and societal good. And his talk is how to do a backflip using nothing but physics.
Today, I'm going to try and do a backflip. Maybe I should think this through first, though. How does a backflip actually work? You go up and you spin and you come back down. Physics. That's the answer. So I need to get up in the air as high as I can. If I break that into 3 problems, I need to get up in the air, I need to turn, and I need to come back down. So gravity is the force that's going to pull me back down. So I need to generate some force upwards to get me as high as possible before I spin. So I can generate a force with my legs. I can generate some force with my body. And I can generate some force with my arms. And if I time it right, I should be able to add them all together to get me as high as possible. Okay, hopefully that looked pretty good. But I can only jump so high. What happens if I don't get around in time? I'm gonna land on my head. So I need to turn as fast as possible. Right, so I need to generate a force to start me turning with my legs and my arms. But how do I make myself turn faster? Have you ever been on a carousel? Those little merry-go-round things at the playground? And you're spinning, and then you pull yourself in and you turn way faster? I think that's the principle we're gonna use here. So if I try this, I generate some force with my arms, I don't spin so fast. But if I generate a force and I pull my arms in, I'll turn way faster. Well, why is that? So I've generated a force that gives my arms some momentum, traveling in a big circle. But then I pull them in, they have a smaller circle to travel around, so they'll travel faster since they have the same momentum. And one last thing. I'm going to generate a force turn myself this way, so I'm going to turn around this point. So if I raise my turning point as high as possible, then I'll have more time before I fall. So how about I start at a height? Add the forces together to get as high as possible. Tuck tight to spin fast and start at a height. Let's give it a go. I'll use this wall. And that's the physics of a backflip.
I don't know about everyone else, but I was genuinely nervous as to whether or not he'd make it there at the end. And I think I'd need divine intervention more than physics to manage a backflip. But we'll flip Adam into this to have him chat with our judges and to see what they have to say about his talk. Aisling, I'll start with you. Any questions for Adam?
Yeah, super. Well done, Adam, on the talk and also managing the backflip. Very impressive. My question is, I'm trying to imagine we were in science gallery. Obviously we're not, but if you had been, I'm wondering how you came to this idea, was it kind of started with the backflip or kind of wanting to describe it, and kind of how you decided to do that as your piece of storytelling?
I suppose it kind of comes from my daily life. I do a lot of these probably stupid things on a daily basis, but I'm also naturally curious. The reason I got into physics in the first place was no one could explain to me how magnetism worked. Like, how did these magnets just stick on the fridge? So I love understanding how things work. And I thought this was a practical example of, if you understand how it works, you can do something really cool with that understanding.
Can I ask a follow-up question then? Did you just learn how to do backflips for this?
No, thankfully. I mean, that would have been real dedication if I had. I am learning how to do front flips at the moment, but thankfully, I thought, for the sake of not scaring my mother when she's watching this, that it wouldn't be the best idea to just learn it on the spot. I've done a few before this.
Well researched. Well done.
Thanks.
And Owen, over to you. Can we get a question from you, please?
Yes, thanks, Adam. And Adam, nice flip there. Adam, I was just thinking, just as Aisling was kind of asking her question, that, one, I guess, of the big struggles is often with physics, maybe because some of the thinking can be so abstract in it, and mathematically even, people find it difficult to connect an everyday event like a backflip, or maybe not everyday event, but, maybe for yourself, and a science like physics. Do you think, if you were to, you've obviously done a really good job of connecting these. Do you think, how would you go about, in general, if you wanted to take another physics topic and connect it to an everyday event? Is there kind of a pattern you'd advise someone to do? Because I think it's something that, a teacher or a lecturer or someone would find really useful. What would be the process you'd go through?
I suppose the way I think about it is the way I used to approach teaching. I tutored for a while, and I think most understanding about physics or any topic is built on some sort of previous understanding. So metaphors are great when understanding complex physics problems, because this is something tactile that I can understand. I think there's a really interesting anecdote. Richard Feynman, famous physicist, received a Nobel Prize for his work in quantum field theory. And he came up with one of the cornerstones of that theory by spinning a plate in the cafeteria and thinking about angular momentum. So I think the bottom line is, you can understand anything if you have something that you can relate it to that you've already understood.
Yeah, that's great. That's great. Thanks, Adam.
Thanks.
Thanks to Adam, and thanks to our judges there. Thanks so much. We will move on to our fourth talk now, and our fourth talk comes from Kira Bozang. Kira is an environmental researcher who is passionate about producing food more sustainably. She has commenced her PhD at University College Dublin in 2017, and her research uses life cycle assessment to understand impacts associated with the life cycle of a product, process, or service. She recently joined Chagask as a postdoctoral researcher, and her talk title is "Why Do Science Need Models?"
do scientists use models? If I ask you to picture a scientist, what comes to mind? Well, if you search on Google Images, you'll see pictures of people wearing white coats, working in a lab, looking down microscopes. But I'm a scientist, and when I start work, I turn on my computer. Because, like many other scientists, my work doesn't include experiments in a lab. Instead, I use models. But what is a model? A model is a simple representation of reality. It helps us to understand how something works or will work. Models are made possible by mathematics to represent the real world in some way. It's a little bit like a video game, where the virtual world is a process, like a weather system or an ocean current system. In the virtual world of a model, we can test lots of different scenarios to see what the outcome can be. And just like a video game, models aren't exactly like the real world. Models are not, nor ever will be, perfect. But they're a great way to carry out experiments that would otherwise be impossible to run. Say, for example, you want to find out the amount of greenhouse gas emissions that are released from cattle in Ireland. We can use sensors to measure the emissions from each animal. But in Ireland, we have 7 million cattle, compared to 5 million people. Even if every person in Ireland was to measure the emissions from one animal, we would still have 2 million animals left over. Obviously, this would be a very time-consuming and expensive way to get this information. Thankfully, we have models. In order to get the necessary information, we only need to measure the emissions from a small sample of animals in the population. We then use a model to combine this with other information, like the number of different types of cattle, calves, cows, bulls, steers, and heifers, to estimate the total amount of emissions. Models are only ever as good as the information you put into them. If your model has a clearly defined purpose, is a good representation of reality, and you understand its limitations, then you have a useful model. With models, we can even answer questions about the future. No crystal ball required. For example, what are the likely impacts of introducing a technology to reduce greenhouse gas emissions? This is why maths is so important to science. So, the next time you picture a scientist, you can think of someone like me, working at my computer, because, like microscopes and white coats, models are another crucial tool for scientists to generate information.
Thank you, Ciara, for that. I think model is one of those words that scientists just all mean the same thing and mean something completely different from not scientists when they use it. Let's bring Ciara into the talk now, and she will be under the judges' spotlight and answer some of their questions. So, Maria, we'll come to you first. Can we get your thoughts and any questions you have?
Thanks very much, Ciara. That was really interesting and an unusual topic for a talk, even though it's something so many scientists use all the time. So I was just wondering, you were saying that your research involves models, but what led you to pick this particular title for your talk?
Yeah, I think I picked this title because it came to the end of my PhD and I was getting ready to defend it. And I kind of came to the realization that I had taken, the model that I used for granted in the past 4 years. So I use life cycle assessment for my research. And in that, we need to look at, aspects of technology, and we also need to look at aspects of the environment. And life cycle assessment, we're able to do that using algebra. Now, I don't actually need to use the algebra myself. I can use a software, and it carries it out for me automatically. But I just came to the realization that I didn't really appreciate what was going on in the background of my software and what was allowing me to get the results that I was getting.
And what about you, Owen? Can we get a quick question from you?
Yeah, thanks, Ciara. I think, you obviously used the word model to try and, draw in people's attention, make them think you were going to talk about something else. And is that something you think is there problems in science that people think that there is no models in science, as in the way the most of the world think of the word model? You think, is that something that's difficult being in science,
I suppose, even again, coming from my own perspective, the fact that I was taking it for granted, and it took me until the end of my PhD to kind of really ask the question, what is a model? And I think, they're very simple examples of models. I mean, if we think, and going back to the comparison to something like a video game, that's something that's very accessible to a lot of people. And even if we don't really understand what's going on in the background, we can appreciate the mathematics that we use to bring it to life. So I think it comes back to scientists maybe, just taking that step to explain what we mean by a model. And obviously models can take many different shapes and forms, and we use them in all aspects of science, but, communicating that a little bit better, I think, would help the general public.
Brilliant. Thanks very much. We got a little bit philosophical there. That was great. Thanks so much, Ciara, and to our judges. Right, that marks the halfway point. We've gone through half our contestants and they've been great. And I'd say the other half are going to be just as great. It's going to be a tough one for our judges to put this through. But let's move on to our fifth talk. And our fifth talk comes from Stella Choi. Stella Choi is a PhD candidate at the School of Education in Trinity College, Dublin. She obtained her master's degree in counselling in 2008 at the University of Hong Kong, and her research interests include inclusive education for children with ASD and anxiety. And her talk title is When a Flower Does Not Bloom, We Care More About Anxiety in Children.
When a flower doesn't bloom, you face the environment in which it grows, not the flower. We can apply this famous quote to early childhood education. But when it comes to children's well-being, and more specifically anxiety in children, the story is totally different. Many of you may think that young children don't have anxiety. In fact, studies show that anxiety disorder is one of the most common mental health problems in children below age 12. The onset could be as young as before age 5. For the past decades, we still don't know a single cause of anxiety disorder. However, we know that it is a combination of 3 factors: genetic, inborn temperament, and environment, such as parenting and life stresses. In Ireland and around the world, the current available service for children with anxiety is addressing the body and mind, medication, and psychological talking therapy. The problem is that it is a very long waiting time if the service is restricted to certain specialists. For example, in COVID, the RTE News reported that a 7-year-old girl with severe anxiety has to wait for 5 years in order to receive the service. We propose that for young children, a play approach using Lego bricks would be more appropriate to address the children's needs. And can we think of a system that is more considering the environmental factors and not limited to certain specialists? For example, we can involve the children's peers in building the Lego bricks together. And we can also involve the whole school storybook reading about the coping of anxiety. We can also think of parents in the parenting groups, and also the teachers and different professionals in the environment, such as professionals in the mental health, education, and disability services. That is, understanding anxiety is everyone's business. Why should anyone care? Because we want the children, our future, to bloom, just like you and me. Thank you.
Thank you so much, Stella, for that. I think the blow-away fact for me there was kids wait 5 years for treatment. That surprised me. But let's move on to the questions now, and we'll bring our judges in, and we'll bring Stella in as well. So, Owen, let's start with you. What do you have?
Thanks, Stella. That was great. Yeah, I mean, like the Adam just touched on there with the comments, it's very, worrying that children that young are waiting, so long to receive really important treatment. I mean, what do you think needs to be done from people like yourselves, researchers, to try and get to the policy makers and decision makers? What can be done to try and cut down this time for treatment?
Thank you for the question. That's a good one. And I think what I propose is we still don't know a lot of things, and we we are learning on the way, and then we propose that because traditionally the treatment for anxiety disorder for children is only the psychiatric doctor and the psychologist. So I get into touch with the training for Lego-based therapy that could involve some teaching professionals and different people in different fields. They learn that approach in one day, and so that they can also use this approach in their work, so that we come up with the idea of involving as many people as possible to understand anxiety more and to use some approach that is play-based, so that everybody can use it in their own work, not just restricted to some doctors or psychologists. Thank you.
Okay. Thank you.
And Aisling, over to you as well.
Yeah, thanks so much for that. I really like the analogy of the plant, and that if the plant isn't growing, that you kind of look at the environment it's in. I'm interested, are there tools to kind of be able to look or measure kind of the impact that environment has in these situations?
Tools. That's a very good question as well. We are also looking for some objective measurement, but human and children are very complex. I always think of some neuroscience or some biofeedback measurement, but I think now we will most likely look for some combination of some qualitative measurement and some objective measurement. And what is new is that we can think of the participant as co-researcher, because traditionally we always think researchers are very high on the hierarchy, but now we think that the children can teach us a lot of things, so that we will involve them in the design and in the research, so that we can learn from them. So that is kind of some new way of doing the research. Thank you.
Thanks there to our judges and to Stella. Thank you. So we will move on with our next talk, and our talk number 6. He studies applied and computational mathematics at UCD and is currently doing his PhD in genomics data science. His project looks at the role of genetic burden in kidney disease and kidney transplant outcomes. His name is Kane Collins, and his talk is Quantum Darts.
So today I'm going to talk to you about one of the weirdest areas of physics, quantum mechanics. You may have heard something about a cat being both dead and alive, or even how quantum computers are going to change the world. But the real physics is even stranger and less cruel to cats. First, let's talk about one of the most well-known experiments in physics, the double slit experiment. Picture a wall with 2 slits in it and another wall behind that. Now imagine throwing darts randomly at the wall, much like I do when playing actual darts. Some will hit the first wall, but some will make it through the slits and hit the back wall in roughly the same shape as the slits. Now, if we take electrons and shoot them through a similar setup, we would expect the same type of pattern, right? Well, it turns out this is not what happens. Instead, what we see is a pattern of bright and dark spots, where the electrons hit the wall in what we call an interference pattern. We see this even if we slow the whole thing down and fire the electrons one at a time. The electron is behaving as if it is a wave, by going through both slits at once and interfering with itself. But this is really strange, because we know that an electron is a particle. And we see this not only in electrons, but also in atoms and even molecules containing hundreds of atoms. Well then, you might ask, why does this not happen to me when I go through a door? Well, I have left out one tiny detail of this experiment. The size of the gap must be similar to the size of the wavelength of the object, and larger objects have smaller wavelengths, and so would require impossibly small gaps. However, there is no reason that we cannot, in principle, do this experiment with larger objects, such as viruses. But our strange experiment gets even stranger. Suppose we want to figure out which slit the electron goes through, and we set up a detector beside the slit. Then the interference pattern will disappear and be replaced by the darts-like pattern. It is as if the electron knows that we are watching it. So what have we learned from all of this? Well, Matter can act like both particles and waves, and also that the act of observing a quantum system has a fundamental effect on that system. One interpretation of all of this is that a quantum particle doesn't exist in one state or another, but in all possible states at once. It is only when we observe its state the particle is forced to choose one possibility. This is a pretty profound philosophical idea. Now, think about that next time you play darts.
That was Kane there, and thanks, Kane. You could spend an entire lecture course explaining to people one aspect of quantum mechanics, so well done for getting it out in 3 minutes. But it's not over for Kane just yet. Let's bring him in with our judges and we'll get some thoughts and comments from them. So we will start with Maria this time. Maria, what do you think?
Thanks very much, Kane. That was really interesting. I was just wondering, it's quite different from what you're researching, just from the initial bio. So what made you be interested in quantum darts?
Well, so I did my undergraduate degree in applied and computational mathematics. So we studied a lot of quantum mechanics during that course. I'm now doing genomics data science, so quite different. But basically, kind of what made me choose this was because I thought it was a very interesting topic, and while we went quite in depth into it in college, and I could solve quite complex mathematical equations, I was thinking, how do I actually explain this to somebody who's not done 3 or 4 college level courses in it? And I realized that I was actually not able to do so. So I said that would be kind of an interesting challenge to try and explain the double slit experiment in 3 minutes.
And Aisling, what about you?
Yeah, thanks so much for that. Such a complex but intriguing topic. I wonder, when you came to then approaching this topic, what did you want the key kind of takeaway, I suppose, for maybe somebody coming to this cold to be if they were taking something away?
Well, I guess kind of one of the main things would be just kind of that science is interesting, and that physics is very weird, and it's not quite like we would expect it to be. And just, I guess, to kind of, get people interested in physics. I think a lot of the science communication around physics tends to be on kind of astrophysics and, talk about black holes and neutron stars. I think it's just good as well to kind of focus on some of the other interesting aspects of physics and just show how fascinating they can be.
Absolutely. It's not an insignificant reason why I'm a science communicator these days as well. Thank you so much to our judges and to Kane. We will move on to our next talk, and this talk is from Victoria Caballero. Victoria is a chemical engineer from Cordoba, Argentina. Currently, she is working on her PhD developing mathematical models to predict the safety of fermented foods and smoked salmon at TU Dublin. And her talk is titled The Good Taste of Maths.
I want you to do an exercise. Let's close our eyes and think about cucumbers, olives, some salami, slices of Iberic ham. Now, open your eyes. I'm sure you're all hungry by now after these mouth-watering thoughts. However, did you ever wonder what about this particular taste that we like so much? This very nice flavors. Well, what if I tell you that this is all given by the activity of bacteria? Yeah, isn't that crazy? The bacteria that lives in the food take the nutrients present and transform them into substances that are responsible for the flavors that we love so much. This is called fermentation process, and it has been used by the Greeks, Romans, Egyptians back in the days. So it's something that we've known for a while. Now, in this kind of food, not only these harmless bacteria may grow and develop these substances, but also we can find in small amounts sometimes bad bacteria that can cause us diseases. Well, we call them pathogenic bacteria, and this isn't cool, because if we let them grow, we could be in trouble. But don't panic. Don't panic, because the manufacturing processes that we currently have are designed to avoid the growth of pathogenic bacteria or take them to a level so that the food is safe enough to eat. And achieving this wasn't an easy job at all. We have worked a lot, and one of the tools that we have to avoid the growth of pathogenic bacteria is predicting whether this bacteria is going to grow or not. Yeah, and I mean predicting, like in the future, like yes, in the future. And I know what you're thinking. No, I don't have the tarot cards. I don't do magics. I have something that, in my opinion, is even better. Math. Using math and some very fancy equations, I can describe and so predict whether this bacteria is going to grow or not and how it's going to make it. This is very useful, not just to design manufacturing processes that assure us with certain confidence that the food is going to be safe, but also the distribution chain for the food. So now you know, next time you are having salami or some cucumbers, just sit and enjoy, because math is on your side.
Isn't it amazing how many foods we all love we let go off in a controlled manner? Thank you, Victoria. Thank you so much for that. Now, let's bring her in and we'll get some questions from our judges. So, Aisling, we finished with you last time. Let's start with you this time. Do you have any questions for Victoria?
Yeah, thanks so much for that, Victoria. And I enjoyed the kind of engaging the imagination. I felt like I was tasting some of those things at the beginning there. I'm interested as to how, like, why this was kind of the topic that you were passionate about communicating to us today.
Well, good evening to all first. Well, I really want to communicate this because, in my opinion, I think it's an amazing tool, as other participants were saying, that we can actually see the future. Like, we can know what is going to happen. And this is not only applied to food science, we can apply it to many, many, many fields. And this can make processes very efficient. And we can also, like in this particular case, for example, avoid the waste of tons and tons of food. And we know this is a way of eating more sustainable, you know?
And Owen, let's see, what do you have to say for?
Yeah, thanks, Maria. That was really interesting. I was just wondering, because obviously we trust most of the food we get. We see the use by date, we see the best before date, and we trust that the food will last as long as it's in the refrigerated condition it's supposed to be. But sometimes we have cases where food is recalled due to issues. So what goes wrong? I mean, just because you talk about good bacteria, bad, becoming pathogenic, what might go wrong in a situation where they'd have to do a recall from a reputable company?
Well, this is a very big questions, because there are many things that may happen. But just to give you an example, manufacturing processes of every food we eat, not just fermented food, but every food we eat, are very controlled processes. And we have some critical points that we always check and that are very important to check. At the same time, we're human beings, so sometimes these critical points may have problems, maybe the person who was working in this particular part of the manufacturing process wasn't having the best day, made a mistake, so the food got contaminated in some way. And what I mean is that we're speaking about food. It's like nutrients, tons and tons of nutrients for bacteria. So it's like perfect place for them to grow. It's like, if you let them, they will make a party. So this is why it's very important to keep an eye in this parts of the process that are critical.
Thanks, Maria.
And thank you, Victoria, and thank you to our judges there for that.
Thank you.
So we are now on to our final talk, but definitely at least as good as all the others. This is from Marzia Pendina. Marzia graduated in chemistry and technological pharmacy in Italy and has been living in Ireland since 2018. She is a PhD student in University College Dublin, researching a treatment for uveal melanoma, which is a rare cancer in the eye. And her talk is called Mistakes in Steaks.
I was invited to a friend's house for having dinner. She said that she would like to cook an amazing fillet steak. The same recipe she tasted in a fancy restaurant during her holidays. I already knew it was a really bad idea. She cannot even cook toast. Anyway, we started to chit-chat in the balcony while we were waiting for other friend, and suddenly a huge cloud of fog came from the kitchen. The amazing fillet was completely burned. We almost had to call the fireman. But thank God, she had bought another piece of fillet, and our friend took the lead in trying to save our dinner. She also explained that the meat is full of protein, and the protein can react to change of the temperature, and they can become short. Like a wise clothes, the protein are fully straight when they are full of water. However, if they lose the water, as when you wring the clothes, the structure will be short. But we don't want to lose the water, otherwise the meat would be tough and chewy. So to avoid this, we need to check the temperature with the thermometer. And for the best fillet ever, we need that the Maillard reaction take place. As I mentioned, the meat is full of protein composed of amino acid, and it also has sugar. When the amino acid react with the sugar, he gave to the meat its brown colored and delicious taste. But this can happen only if the surface of the meat reach 140 degrees. Because the reaction is really fast, we need to be ensured that the pan has a high temperature before we put the meat on it. If you do this well, the meat inside will have a temperature of 50 degrees and it will be rare cooked with a lucid and intense red color inside. If you wait 1 minute for each side, you will see that the temperature inside the meat will be 60 degrees, and now the meat is medium rare cooked. But at 70 degrees, in this moment, we lose all the water trapped in the meat, and the meat will be tough, as a lot of steaks that we cook at home. So, if you want to make a really delicious steaks at home, what you need to do is you need to form the component of the Maillard reaction. And if you are wondering how bread becomes toast and food becomes brown and colored, it's also a Maillard reaction. So next time you are deciding to cook a steaks, remember that the temperature are important and keep an eye on your thermometer.
Fitting, isn't it? We started with chocolate going wrong and we end with a superb steak. That seems about right. Thank you so much, Marzia. And now let's get her onto this screen with our 3 judges, the last batch of questions. So we'll start with you, Owen. Can we get a question for Marzia?
Yes, thank you, Marzia. I'll admit, my steak cooking, my techniques can sometimes be brilliant and can sometimes be terrible. So I have no... they're never twice the same. Why is it then? I mean, you've gone through all the steps there, but why do so many of us have such difficulty in cooking a good steak?
Yeah, the glue is just the right temperature where you of your pan. So if your pan has like a low temperature, what can happen is that water inside the meat will be released as soon as in a minute. So you can even cook properly the meat. But if your pan is really hot, even more than 140 degrees, you will be able to cook an amazing steaks. So the temperature is the key of the cooking, actually.
Okay, I'll remember that. Thank you.
And Maria, we'll come to you. You get the privilege of the last question of the heat.
Yeah, it's like food themed for the last one. I haven't had dinner yet, so not very fair. But no, thanks very much. That was a brilliant talk. I was just wondering, how does this reaction have any ties in with other kind of science that you maybe use in manufacturing or drugs or things like that?
So actually, it's like this reaction is a simple reaction where like a carboxyl group of the sugar react with the amino group of like the amino acid. So it's like in everyday life. So when we cook, when we even we bake, or it's characterized on most of like type of reaction. Of course, what can happen is that some of them have like give a different compound at the end. So different compound and associated with different aroma or different smell. So I cannot like say generalize this reaction, but it's like an umbrella of a lot of reaction that can happen while you cook or even when you like create new drug or new compound.
Brilliant. Thank you, Marzia, and thank you to all our judges. So now the judges are going to go off into their own little super secret special breakout room, and they will have the very difficult task of trying to come up with a first and second place. And you at home aren't off the hook either, because you have to pick an audience winner. Coming up on the screen now, there will be a slide with a web address on it. That slide is famelab2021.com. If you go to that, you will be able to pick your favorites from the audience. And just to save your working memory, because it's been a lot of brilliant talks, we have had Rhea Zwane, who talked about the chemistry of shape in chocolate and drugs, Angelique Sherrill, who talked tanning, but beautiful but harmful, Adam Stapleton was telling us how to do a backflip using nothing but physics, Kira Bozang told us why scientists need muzzles, Stella Choi talked about when a flower does not bloom, we care more about anxiety in children, Kane Collins gave us a game of quantum darts, Victoria Caballero talked about the good taste of maths, and Marzia Pendino talked about mistakes in steaks. 8 brilliant talks there, so you've got a real crop to pick from, and good luck to you. I'm glad I just get to sit here and listen and talk about them, and I don't have to pick between them because they're all my favorite. And now we will be moving into an interval while the judges are deliberating. So we're going on a trip down FameLab Ireland memory lane with our interval act from the 2016 national final, Helen Arney. Writer, science presenter, geek songstress, and voice of an angle, Helen has appeared on TV, radio, and in theatres across the world with her unique mix of stand-up, songs, and science. Helen is absolutely brilliant. So sit back and prepare to be entertained even with some great one-liners. Helen Arney, everyone.
So hello, ladies and gentlemen, my name is Helen Arney. I am a musical comedian. I am 1/3 of a show called Festival of the Spoken Nerd. Yes, Jonathan's had a few good puns tonight, but I am aiming to top that. And I'm also someone who does songs about science. Can I find out how many scientists we have in the house? Woo, cool. That is genuinely more than normal at my gigs, but that's fine, just so everyone feels included. Do we get any more scientists if I do that? A few more? A few extra if I do that? Or just anyone who's recently seen an episode of Doctor Who? Just, yeah, full fingers there, yeah. You will actually get a degree if you watch enough Doctor Who. I promise. It is a media studies degree, but it will still inform you in a lot of ways about the world. So what I love to do is I love to write songs about science. That's what I do. I studied science at university. I studied physics at university. And the reason I studied physics was, one, as many of our speakers have mentioned tonight, you get to play with massive lasers. And the second thing is they told me that in my first year, it would be 90% men. 90% men. What they didn't tell me was that although the odds are good, the goods are odd. So that's a little different. Don't applaud that. I'm including myself in the odd category there, so no fear. But what I love to do now is I write songs about science. I'm going to sing 2, or depending on how the judges are doing, 3 songs that are inspired by science. I do a show, Festival of the Spoken Nerd. We've hopefully we'll bring it over to Dublin sometime. It's super fun. I also do a solo show called Helen Arnie, Voice of an Angle. Just checking. Jonathan loved that. A lot of you in the room weren't so sure. I always like doing a really nerdy maths pun at the beginning of my set because it kind of draws a line through the audience. If you enjoyed that, this whole set will give you a large hadron. Good. That draws a different line through the audience. That line is 27 kilometers long and under Geneva. Good. So I'm going to do a song for you that is inspired. Do you mind if I pull you off this screen? Is that all right? You've all got it. If you haven't got it by now, I think there's no hope for any of us. But what I want to do is do a song that I wrote for Radio 4 show, BBC Radio 4 show called Infinite Monkey Cage. I'm sure many of you listen to it here on illegal bootleg. I can't even watch my own show Eureka in the UK because it's on RTE. Darn you. But I was inspired to write this song for that show for a very specific reason. I found this, hopefully, on YouTube. Now, YouTube is where I go for all my science news, because a lot of you who are over 15 are looking at me really skeptically. But no, YouTube is where the science news is. How else would we know that cats can play the piano? Seriously, it's brilliant. So what I did was I found the NASA YouTube website. Now, NASA has its own YouTube channel, and it has videos of things like this. Now, some of you may not recognize it. Does anyone know? I know it doesn't make a lot of appearances in Ireland, but yeah, it's the sun. You were mouthing it, I bet. It's the sun. And this isn't just a still picture. This is a video from the NASA website of something called a coronal mass ejection, a sunspot explosion. I'll see if I can trigger it off. Yeah. I mean, I added the sound effect. But that's what it is. That's what happens. Our sun is not just a ball of gas in the sky. Our sun is doing stuff like, it's doing an impression of a peach farting on a regular basis. And it does this, and it's absolutely bonkers. And this worries me, because they were uploading more and more of these every month on the actual NASA website. And I started worrying that this was the moment I should be planning to excavate my basement, fill it with baked beans, cover myself in tinfoil, and work out how I can repopulate Earth with just me and members of Westlife. I just think they'd be good breeding stock in an emergency, right? And I just thought, this is the end. And I had to speak to one of my friends who was a solar physicist, and she showed me a graph, and she explained to me that what happens is the sun is not just a static ball of gas. It's a thing that things happen on that surface. And those solar explosions, they cause the aurora borealis, they cause the northern lights. But they can also do things like knock out satellites, they can break our electrical systems. But the sun is in this weird 11-year cycle. It gets more active, gets less active. It gets more active, gets less active. And we happen to be in one of those periods where it's getting more active. And to be honest, at this point, I wasn't really listening. Because I'd already made up my own mind. I decided that the sun is not happy about all these television programs that people are making, about other parts of the galaxy, those distant comets, those parts of the universe that are, being I'm very angry about this, being pointed at by floppy-haired Mancunian professors who I think you know who I mean. So my theory is that the sun has got its huff on. Good. I can tell exactly how many fans of 1930s musicals are in. I used to be someone. Now I'm just another son. One of 100,000 billion. You treat me insignificantly. You name a tabloid after me. Synonymous with paparazzi. Just a backdrop for Brian Cox on TV. Oh, look at that star. Since Edwin Hubble, it's never been the same. Those pictures of other stars pushed me out of the frame. You never even gave me a proper name. Something like Alpha Centauri or Epsilon Tauri or Delta Libre. At this point, I'll even take HR2948. It's the real name of a star. Or Kevin. You've achieved nuclear fusion. Oh, well done. Made some helium from a little hydrogen. That's very cute, Earth. But every second I do that to 600 million tons. If I was Marilyn Monroe, you'd be the one I can't remember the name of from One Direction, which is all of One Direction, apart from Zayn. You should have stopped at Copernicus. Then I'd still be the center of your universe. You say I'm just an average ball of gas. I say you're talking out of Uranus. I don't know how that's pronounced. I'm the sun. 1.4 million kilometers. That's my diameter. Tell me seriously, with those parameters, have you ever tried to put a hat on there? Hip, 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 hooray. Well, I'll be a red giant someday, and your world will go up in flames. I shouldn't laugh. But in the meantime, please join my Facebook fan page. Seriously, I've only got 9 likes. Well, now it's gone down to 8 because Pluto defriended me. Thanks very much. All right. We have very little time. Now, I want to do a song that is not actually one of mine, and it is inspired by a piece of clothing that I'm wearing right now. A couple of people have already mentioned, they've seen tonight, my periodic table dress. I already had people asking where it's from, people asking what it's made of. It's made of jersey. It's got the entire periodic table on it. It's made of jersey, which means it's completely non-iron, apart from this square here, which is atomic number 26. Keep up, everyone. So don't ask what the noble gases are. They're around the back. I had a lot of jokes about this, but to be honest, Jonathan's made a lot of puns tonight, and the best ones are gone. So I'm going to do this. Some of you might know this song already. This song was written in 1959 by Harvard mathematician and musical comedian Tom Lehrer, and it is 106 elements of the periodic table set to a theme by Gilbert and Sullivan. And this has been so difficult to learn that I've had to lose bits of information that I used to know. I feel incredibly jealous of all of the FameLab candidates for remembering their talk. Seriously, I no longer know where I live, my parents' phone number, or what my husband looks like. All of these things are now gone. I mean, he could be here tonight. I don't know. Any volunteers? So, no, it's fine. So I've got a photo on my phone. It's all right. I'm going to try and do this song for you. Now, sometimes I do make a few mistakes. If you hear a new element like oopstonium, that's where I've gone wrong. But let's make it a bit more interesting tonight. FameLab, it's all very interactive tonight. So let me ask you to cheer on your favourite element. Now, only 5% of you have come prepared with a favourite element. That's fine. I look forward to finding out what your favourite element is. About 4 elements after I sing it. It goes very fast. But if you don't have a favourite element, your favourite element now is sodium. Okay, your favourite element is sodium. It's a great element. It's one of the most abundant elements in the sun. When you hear sodium, go crazy. Clap, applaud, jump out of your seats, mind the cameras. Just make sure you carry me around the room on your shoulders really safely. And by the way, sodium is the last element of the song. So basically, here's a tip for you FameLabbers. Give yourself a standing ovation. That's it. That's how to do it, guys. So we're going to do this. I'm going to desperately try and remember this. It's going to be a bit of a challenge. We're going to start quite slowly, but let us give it a try. By the way, can everyone hear the ukulele? Can everyone? Yeah, I'm really sorry about that. Here we go. Tom Lehrer Elements. Here we go. 106 elements. La 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 la. There's some chemists thinking, is she just going to sing Lanthanum repeatedly 106 times? Don't worry, I'm not going to get away with that. Here we go. There's antimony, arsenic, aluminum. Is someone singing along? If you want to sing along, please don't. You might get it more right than me. There's someone was in there early. There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, and protactinium, and indium, and gallium. That's genuinely the best cheer I've ever had at any point in this song. And iodine and thorium and thulium and thallium. La 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 la. Guys, you were prepared. Rest of you, you're just waiting for sodium, aren't you? There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. La 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 la. Did I do oxygen a long time ago? Because I have run out. Okay, by the way, that last verse, the biggest cheer I've ever had in my career was when I did this song at the NHS Leeds Gastroenterology Department. And when I sang the word barium, they went crazy. All right, let's do this. Okay, let's do this a little bit faster. Here we go. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury and molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium. Which, if you get poisoned by it, makes you smell of garlic. And cadmium and calcium and chromium and curium. La 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 la. Okay, this is the last bit. I need you to help me out a little bit by clapping along slowly. And we're going to get this in. Here we go. Sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, zinc, and zinc, and rhodium, and chlorine, carbon, copper, tungsten, tin, and sodium. I need to let you know that unfortunately, since this was written in 1959, they've discovered 13 more elements. And I can give you a choice now. I can either attempt to sing them for you now, which will mean that I will no longer be able to remember my flight home tomorrow, or I can do the cop-out version. Do you want the full elements or the cop-out version? Full elements? Cop-out version. Yeah. The FameLab is helping me out. They know how hard it is up here. Okay, I'll try. Okay, I'll try. Here we go. Genuinely, you can see this, a version of this on Eureka, the Big Bang Career on RTE2 on a couple of Mondays' time. And I will probably do a slightly better version of it now. Because I have remembered to learn it. Here we go. There's lawrencium, meitnerium, darmstadium, seaborgium, roentgenium, and dublium, and fluorovium, and borium, copernicium, livermorium, and hassium, rutherfordium, anuntrium, anunpentium, anunseptium, anunoctium. Those are the worst element names ever. But it's fine. They just haven't had their names yet from a chemistry consortium. Suggestions, welcome. We good? Great. Ladies and gentlemen, thank you so much. I had another song planned, but you will have to go to my YouTube page and watch them all instead, because I'm going to hand over to finally find out the winner of tonight's competition. It's been an absolute pleasure to come and be part of this. Congratulations, you are all absolute winners, and it's been a total pleasure. Thank you very much. I hope we'll be back soon.
Well done.
Thank you, Helen. Isn't Helen brilliant? An absolute star, because that's what she was talking about in her interval there. Absolutely brilliant. Now, our judges are back from their very difficult deliberations. So let's put them in the spotlight and bring them front and center. So, Owen, I believe you've been appointed or perhaps shoved into this role. How did you find that? How was that picking a winner? And what did you think of the evening?
It was very difficult, Adam. First of all, a good difficult though, because the quality was extremely high. I thought, all 8 speakers, contestants were brilliant. With the 3 of us did, not just me, and we used every single second of every single minute we were given to deliberate on that and come to our judgment. It wasn't easy, but we really trashed it out and we went through everyone in the end. We thought all of them were excellent, and we just wanted to say as well, and I suppose, Adam, having come through FameLab and how challenging it is. I guess we did it on stage in front of an audience, but these contestants and these FameLab speakers have had to adjust to Zoom. And what we really thought was excellent was how they kind of embraced that transition and found ways of, just making the changes which fitted this format here. Saying just wanted to comment on that we thought that was really excellent. Also the variety of approaches which people took, the use of props within that. I just thought there was a real nice mix within it tonight, and just well done to everyone. And it wasn't an easy, really, really well done.
Thank you very much, and thank you to you judges as well. That it's not an easy thing to come up with questions on the spot every time I come and put the spotlight on you, and it's not easy to pick a winner either. So thank you so much for being a part of this. So now we're here. We have our judges, we have our talks, we've done everything. There is nothing left to do but the announcements. The first thing is the audience prize that you have been voting on. That will be announced somewhere in the chat. There. I don't know. I don't see it. But well done to the audience winner, whoever they are. You've won the hearts of the people. And in the end, isn't that the real victory? But as for our judges, what have they said? Well, our runner-up for this evening, and at home, I want you all doing a drum roll on your table, and I'll know if you're not doing it. Our runner-up is Adam Stapleton. So, congrats to you, Adam. That garden backflip played off, didn't it?
Thanks so much. Yeah, it looks like the effort in endangering my life paid off.
And isn't that it? That's why we endanger our lives, to communicate science. Yeah. Thank you. Thank you very much, Adam.
Thanks so much, Adam. And thanks to the judges, and well done to all the other contestants as well. Really great talk.
And finally, last thing we've got to announce is the actual winner. So an even bigger drum roll this time, and I'm even more going to know if you're not doing it. And our winner tonight of the first of our 2 Dublin heats is Rhea Zwane. Congratulations, Rhea. Congratulations. Well done.
Oh, thank you so much.
So can you tell us just quickly how you're feeling?
I'm so thrilled because it's my first science communication experience, and I've had such a lot of fun doing it, and I enjoyed all the other talks really genuinely. Yeah, I'm thrilled.
Brilliant. Thank you so much, Rhea, and congratulations as well on a brilliant talk and on winning the first of our Dublin heats. Well done. You. And we are at the end of our evening. So thank yous are in order. Thank you to all of our contestants for putting together 8 really incredible talks, for our judges who had the arduous task of choosing between them and being in the spotlight whenever I annoyed them. And of course, to all of you at home for watching and commenting and being involved. There is a survey link that you can fill out that is at the same link as you voted earlier for the audience vote. That will be somewhere on the screen now. So if you could please go to that and fill out the survey, it would be a really massive help to us. And then the last people to thank are the main partners, the British Council and the Cheltenham Science Festival, the main funders who are SFI, and then the supporters as well, who are CPL and Henkel. Thank you so much. Thank you all for being here. Please join us again for the next Dublin Heat next week on the 24th. Thanks again. Have a good night and goodbye.